In this lesson, we're going to continue our examination of counting techniques. We're going to start off by looking at situations where we have different orders, and we need to put things into those different orders. So we'll start with a little example here. So we have two people, and this old man and this little girl's skipping rope. And I want to know how many different ways can they line up in a row. Okay, well, obviously we have the first example right here. We have the old man and the little girl, but it also could have been the little girl and the old man. There's only two possibilities. There's two of them. Okay. If we have three people, however, we have the old man, the little girl, and then we have the second little girl, how many ways can we line them up? Well, we could have the old man first, and then we can switch the order of the girls. Or we can put the little girl first, and then the old man, and then the little girl. Or again, we could have the little girl first, and then that, and then that. Or we could start with the third one. And we have that situation. Or, again, we have the first choice, and then our second choice, and then our third choice. Okay? And I can see by looking at these visuals that there's 6 of them. Now, we can keep doing this. We could try and line up 4 people, and then 5 people, and then 6 people. And we could keep trying to play with the shapes, but we want to think about the idea of the situation. If we have 4 people, what do we have to decide first? Well, we got to decide which of the 4 is going to go in the first spot. And there's 4 choices there. Once I use up a person, let's pretend this little girl went first. Well, now she's gone. She's not over here anymore. I've got 3 people to choose from. Again, I can pick somebody and they go in that spot. Once they're gone, they're used up. I've got 2 people and then 1 person. And because I have to do the first person and the second and the third and the fourth, I need to multiply. If we go back for a second to the 2 previous ones, really this was 3 choices and then 2 choices and then 1 choice. And back one more stage, it was 2 choices and 1 choice. Okay. So these situations where we have a select group of items and we want to put them in order in a row are a series of consecutive integers. Okay. When we come across a situation like this, a series of consecutive integers, we can simplify it. We don't have to write out 4 times 3 times 2 times 1, or if there was 10 people, 10 times 9 times 8 times 8, 7 times 6 times 5 times 4 times 3 times 2 times 1. We can use some notation. We call this notation a factorial. Here's a factorial notation, n factorial. What that means is, for instance, 4 people, you start at n, the 4 of them, and then you do 1 less than that, and then 1 less than that, and then 1 less than that, all the way down to you come to the 1, which in this case would just be the next one. Okay. It's simplifying the process of writing out this series of consecutive integers. Now the nice thing is this is a button on your calculator. On our calculator we'll often see x factorial, but it could be the n. Okay. You're going to have to find that button on your calculator. We're going to try and make use of it. So let's try some with our calculators to make sure we know what's going on here. 3 factorial. What does that mean? It means 3 times 2 times 1, but if we try with our calculator, we should just get 6. 8 factorial. So 8, 7, 6, 5, 4, 3, 2, 1. I don't want do that by hand. I'm typing my calculator 8 factorial. If I do it properly, I should get 40,320. Okay, we can do operations of factorials. You can type this in just the way it looks. 7 factorial divided by 4 factorial. And you should get 210. And then we can try the last one with these really big numbers, 100 factorial divided by 99 factorial. And if you try this with your calculator, you're probably going to get an error. In fact, I can guarantee you're going to get an error because these numbers are too big for your calculator. 100 factorial means 100 times 99 times 98 times 97, all the way down to 1. That's a huge number. Your calculator can't handle that. But here's kind of a nice thing. Your brain can, if you stop and think about what a factorial means. And to do that, I'm going to go back to letter C. 7 factorial really means 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. And one of the things we've learned in previous math courses is if I have the same number on the top and the bottom of a fraction and they're multiplying, which these are, I can cancel them out. In other words, 1 with a 1, 2 with a 2, 3 with a 3, 4 with a 4, and I'm left with 7 times 6 times 5, which comes out to 210. And if I use the idea in the next one, what does this really mean? 100, we said, times 99 times 98 times dot, 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 divided by 99 times 98 times dot, 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 dot. I can cancel. And I know this answer comes up to 100. And I don't need my calculator to do that, but if I understand the idea of a factorial, I can. Okay, when do we use factorials? And that's one of our tricky things with counting is, how do I know what to use and when to use it? So how do I know when to use this? Well, there's three things that have to be true. I have to be using all of the items. I have to line up all the people. I can only use one thing, each thing once. So a person can't be standing at the front of the line and the back of the line, because I can't repeat. And order has to matter. Okay, the numbers 1, 2, 3 is different than 2, 3, 1. Order matters. Okay, so for example, our class has 24 people in it. How many different ways can we line that up in order? Well, each person in the class is going to be used. I'm going to put them all in a row. We're only going to use them once. Each person, once they're in line, they can't move. And order matters. If you're at the front of the line or if you're seventh in the line, those are different things. So this is a factorial question, 24 factorial. This comes up to a giant number, 6.204 times 10 to the power of 23. In other words, 6204, that's 3 spots, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 22, 23. Okay, this is how many different orders we can put the class in, which would take us a little bit of time. Okay. For my purposes, I would prefer you guys just give me scientific notation. Just want to talk about what that number means. Okay, so let's look at some examples where we can use this. So we got Emilio. He's going to university next year. He has to go buy his books for all his classes. He's got 7 different classes. I want to know how many different ways he can arrange them on his bookshelves. If we have some conditions here. There are no restrictions. In other words, he can put them in whatever order he wants to. Well, if he can put things in whatever order he wants to, these can all be moved around, right? Doesn't matter what order they go in, not a big deal. Move this one over here, this one over here. He's got 7 books. He's got to put them all on a shelf. He's using them all. He's not repeating any books. There's no books that show up twice. And order matters. I can tell French, art, physics apart from art, physics, French. That's a different order. So this is a factorial question. 7 factorial, 7 books. So our answer is 50/40. And this is all the math you have to show. The math in this course is often very, very short. The thinking is going to be our trick. Okay, the thinking's big, the math is small. Let's try part B. French and English must be side by side. So in other words, the order I have them in right now won't work because French and English are split by physics. So I have to be able to move these around, put the French and English side by side. So for instance, oops, there's one example where French and English are together at one of the orders. So there's a restriction this time. To do this question, here's what we need to think about. We need to think about French and English being its own subgroup. So I'm going to group these two things. Okay? And I'm going to move that group around. So really what I have to arrange is I've got these 5 individual books plus this group, which makes a total of 6 objects. So I've got 6 things that have to be arranged. But here's the second tricky part. This group that we have, French-English, doesn't have to be in the order French-English. It could be English-French. So I already have the 6 things, the group plus the 5 individuals, and, well, there's that word again, and multiply this small subgroup, the French-English group. It can be arranged 2 factorial ways, French-English or English-French. So there's 2 parts to this question. There's the overall arrangement and there's the subgroup arrangement. That comes out to 14/40. Okay. I know this is not the next question, but just to point out, if you had three things to arrange, let's say calculus had to be with them also. Well, you'd have this group of three, we'd group it. So we'd have the group plus 4 individual, which makes 5 factorial things. And the group itself can be arranged in 3 factorial ways. All right, let's do part C. Same question, still continuing. Part C. French and English cannot be together. Okay. Well, we figured out the ways they are together. It's actually really easy to figure out the ways they're not together, because those are complementary events. They're either together or not. Well, that's all the different ways. In other words, that's our total. Right? There's no choices, either together or not. And we know together is 1440. And we know the total is 5040. So if I want to figure out the ones that are not together, my not will be 5040 minus together. And this will be my not, which gives us 3600. So we're back to the idea of complement, the idea of sets, Venn diagrams. Those things all go together. We're just using it for counting now. Okay, we're going to try some more examples. We can use factorials. How many different orders can 8 students present their projects if John is first and Linda is last? So here's our projects. We've got 8 students, 4, 5, 6, 7, 8. John has to go first. Linda has to go last. Well, the idea I need you to think about here is that if John goes first and Linda goes last, those aren't really selections. Those things are kind of like they're filled in. Don't have a choice on those. All I really need to worry about is the stuff in the middle. In fact, anytime we have restrictions like this, if a spot must be filled in a particular way, fill it first. And then ignore it. Those spots don't matter. It's not like they don't even exist anymore. All we care about is these 6 spots in the middle. How many ways can I fill these 6 spots? 6 factorial. I'm filling all of them. Each person is different, and order matters. Okay, if we take that idea and look at the second one, letter B, Jody has to be third. Well, Jody has to be third. Again, it's a specific spot that I got to fill. I got Jody in third. I don't really care about her spot anymore. It's been filled. It's done. It's done, right? Well, I need 8 spots. So I've got 7 ways of doing this one and 6. Let's skip Jody's spot. 5, 4, 3, 2. Well, that's just 7 factorial. In other words, 5040. Okay, so if you have a thing that needs to be filled, we did this kind of yesterday when we said we had 4-digit numbers. That had to start with the number 4. We filled it in. We took care of it. Once it's done, it's done. All right, our second idea for today. So factorials, let's take that a step further. We're going to look at permutations next. A permutation is a special version of a factorial. It's an arrangement of a collection of things. But you're not going to arrange all of the things anymore. You're going to select some of them. Okay, so if there's n objects altogether, we're going to fill r spots. So for instance, we have 10 people, and we want to put 4 of them in order. The first 4 spots. Okay, who's going to be first, who's going to be second, who's going to be third, who's going to be fourth? Well, I don't want to do 10 factorial anymore, because I don't need all of the people. I only need 4 spots. So we have a permutation button on our calculator. It looks like NPR. And what it does for us is it takes all of the objects and it arranges some of them. And that's how this formula works. Now, you don't have to do the formula. I'm not going to ask you to calculate things by hand. Use your NPR button. Okay, but we want to know where it comes from. So let's try this first example. Explain what 12p3 actually means. Well, 12p3 means there's 12 objects. That's the first number, the n. And 3 spots to fill. Okay, so first, second, and third. I've got 12 people to choose from. Who came first, who came second, who came third? That's a permutation. Using the button on your calculator, you put the 12 in first, and then the P, and then the 3. I've got my calculator here, and you should get, let's see what I got here, 12P3. 3. Make sure you're using one that has a P in it. There's also one that has a C in it. That means something different. We'll look at that later. You should get 1320. And let's examine some questions that deal with these. So, rewrite using permutation notation. So 14 times 13 times 12 times 11, that looks like a series of numbers, but it's not all the numbers, it's only the first 4 numbers. So in permutation notation, there were 14 objects, if this kept on going, but I only filled the first 4 spots, so 14p4. Okay, an investment club, 5 members, wants to select a president and a vice president. How many ways can this be done? So I've got a group of 5 things, but I only want to fill 2 spots. Okay? Not a factorial, it's a permutation. I can tell the president and vice president apart, which means there's still order involved here. How do I do this? 5p2. And that gives us 20. Try the next one. A sailboat race has boats from 12 different countries. How many ways can I get with the first, second, and third place trophies? Again, I'm not filling up all of them. I'm only filling out 3 spots. There's 12 choices. I need to fill in 3 spots. So 12p3. That comes up to 1320. And I do want to see, this is your notation, okay, and your answer. I want to see both. And a couple more. How many 4-digit numbers, ooh, we've done this kind of thing before, are possible with 3, 4, 5, 6, 7, 8, and 9, assuming that no digits repeat? And that's important. That means I can use factorials and permutations. No repetition. Okay, so let's try this. This is kind of like we did yesterday, except for yesterday we went through and counted them, right? Now I'm going to use a permutation. There are 1, 2, 3, 4, 5, 6, 7 numbers, and I'm making a 4-digit number, so 7p4. Okay, 7p4 is 210. How many of these are odd numbers? We did this again yesterday also. Odd means the last digit has to be an odd choice. Odd numbers are those 4. So there's 4 choices here. But I also have to fill the first part. We said yesterday if you use up a number, it's gone. Same thing. So I've got 6 things, and I've got 3 spots. So in other words, 6p3 times the 4 choices, because I got to fill the first part and the second part. So 6p3 times 4 comes up to 480. Right, how about we try the last part there to see how many of these things are even numbers? Well, oh, sorry, this was 2100, sorry, not 210, my fault. Oh, sorry, wrong number. Look at the wrong number altogether. 840. 840. That's a big difference. Sorry. Part C. How many of these things are even numbers? Well, I could do the same idea. I got to end with an even. So I got 4, 6, or 8. That's 3 choices. I got to fill the other 3 digits from the 6 choices. So 6p3 times 3. And if I do that, I get 360. Now, that's not the only way you could have approached that question. The other thing you could have done was think about B and C as being A and A naught. These are complements. They're either even or odd. Now, if we know the total, which we do, 840, so total minus odd numbers, you're going to be left with even numbers. And if you try it, 840 minus 480 gives you 360. So there's 2 ways of doing that one. And the last 2 here. How many arrangements are there of the letters in the word computer if all the vowels must come first? Okay, so we're back to using all of the letters. All of the letters means it's factorial. The only trick here is I need the vowels to come first. So you need a vowel, and a vowel. There's 3 of them. How many ways can I arrange those 3 vowels? 3 factorial. Followed by the consonants. C, M, P, T, and R. 5 of those. So 3 factorial times 5 factorial. So vowels and consonants. And we multiply that together, we get 720. And last one. 5 people are arranged around the table. How many arrangements of people are there if the table is circular? This is the one's a little tricky because it's a circle. Here's the problem with a circle. I'm going to rearrange my people around this table. 1, 2, 3, 4, 5, and they're going to move them all. You ready? They're all moved around, right? They're all in different chairs. But what you might notice is they're still in the same order. Just changing chair doesn't mean you're changing order. The problem with a circle is there's no start and no end. It goes round and round. To be able to count how many options there are when things are in a circle, we have to pick one person and force them to be the start and the end. In other words, you got to pick somebody, it doesn't matter who it is, and say, you can't move. So if person 4 is over here now, I really need to arrange the people around them. I've got 1 chair to fill, 2 chairs to fill, 3 chairs to fill, 4 chairs to fill, because the person number 4 can't move. That chair is stuck. So with things in a circle, there's only 4 things to fill. That's 24. Okay, there's factorials and permutations. Things that have to be put in order. Some of the things, that's a permutation. All of the things, that's a factorial. You gotta try the homework. Here's the questions here. See what you can do. Some of these are probably gonna need some help with. Hey, give them a try. If you're stuck, come see me. And then we're gonna add some more counting techniques in.